welcome back to my YouTube channel, and this is the lecture number 7. And till now I have covered the working of the PLL. So from now we will start looking the individual blocks of the PLL. So the very first block which we are going to discuss is the phase detector block. Okay, phase detector, also we call it PD block. So this phase detector, there is a lot of type of this phase detector. Okay, so it depends on what type of input you are giving to the PLL. It is sinusoidal or it is pulse type of signal. Okay, so that depends on this sinusoidal. So there are, if I'm broadly talking, there are two type of the PLL. One is the mixer type PLL, and then there is a XOR, XOR PL, XOR PD, and more. Okay, so we will talk about other category later. So the first of all, why we are going to the mixer and the XOR. So in mixer, if we are using the sinusoidal input and output for the PD, then we have to multiply these inputs and output for getting the phase error, right? So you can't use for this mixer for pulse, right? Okay, so now let's do our first category, that is a mixer type PD. So that is first mixer. This is analog phase detector. So when your input is sinusoidal and the output is also sinusoidal, that time we use it. Okay, so let me draw it. So this is V in, and this is V out, and this is VPD. So if I'm taking V in sine omega t plus phi in 0, and V out is cos omega t plus phi out 0, then the VPD will be V in into V out, right? So after multiplication of these two, V in and V out, the VPD will be sine 2 omega t plus phi in 0, phi out 0, and plus sine phi in 0 minus phi out 0. Okay. So we can say VPD is equal to 1 by 2 sine 2 omega t plus phi in 0 plus phi out 0. Okay, and plus sine phi error 0. So this is the VPD. So in this VPD, you can see there are two component. One is this, which is high frequency component, and one is this, which is containing only the phase error, right? So this is the VPD. Actually, we only care about the VPD, average of the VPD. We don't care much about this VPD. Why? Because when this VPD will pass through the low pass filter, or which is containing one integrator, it will remove this. It will become 0 after passing through this integrator. Even if you don't have this integrator, the VCO, which is K VCO by S, will do average of it, and this thing will become 0. Okay. So, but okay, I'm drawing the VPD also, how VPD will look. So there were two component in VPD. One was the high frequency, that was 2 omega, and one was sine phi error 0. Okay, these were two parameters inside the VPD was containing these two, and outside the multiplication was with 1 by 2. Okay, so see, if I'm saying if this phi error is constant, then, and if I'm drawing this VPD, then what will happen? This is 2 omega frequency and this is sinusoidal, and this is constant, so it will be shifted by some amount of sine phi error 0. Since we are adding this constant value in this sine signal, so it will be go up by this much. Okay, so it will be like this. This is a high frequency signal. Yeah, so it will be VPD will be like this. But we are not caring about this VPD. We care about the VPD bar, which will change your VC, and this VC will change omega out, and this will change phi out, by which you can decrease your phase error. So if I'm plotting this VPD average, so I told you that this high frequency signal will become 0, and you will got this much only. So VPD bar is equal to, sorry, let me take pen. So it will become 1 by 2 sine phi error 0. If this phi error is varying with time, so the plot of VPD bar will be somewhat like this. This is 0, it is pi by 2, this is pi, minus pi by 2, minus pi. Okay, so you can see that VPD bar is positive for when this is phase error, okay, for phase error 0 to pi, right? And you can see that VPD bar is negative for phi error greater than pi. So if you are going more, so there you can see it is negative, and in this case it is positive. Okay, so that's what I tried to draw, this VPD bar. Now why I'm drawing it, what I want to convey here, so that is this. So let you have some positive phase error is positive. Okay, what does it mean? Phase error is what? Phase error is phi in minus phi out. So since I'm saying that phase error is positive, it means that this is greater than this. Okay, so phi in is greater than phi out. So if you want to make this phase error minimum, or you want to make it 0, you have to increase this. To bring close to phi in, you have to increase phi out. How can you increase phi out? For increasing the phi out, if I'm drawing the circuit, so there was VC, this was KVCO by S, and this was omega out, and then some low pass filter, and this was VPD, and this is the here phase detector. Okay, and we also know that omega, oh yeah, phi out, you want to increase phi out, right? So for increasing phi out, what we have to do, we know that phi out is integration of omega out. Oh, let me raise this, omega out dot dt. So for increasing this, you have to increase omega out. And how can you increase omega out? For this, you have to increase VC. Okay, that means you have to increase VPD bar. I hope it is clear. So what you have to do, you have to stay here for increasing VPD bar, because what is your aim? You want to minimize this phase error. You want to make it 0, or you want to minimize, then you have to stay here in this linear region. If you are going in this region here, where you can see this phase error, in which you can see that VPD bar is reducing. Okay, if the VPD bar is reducing, then what will happen? VPD bar is reducing, then your VC will reducing. If VC is reducing, means omega out is reducing. If omega out is reducing, means phi out is reducing. And if phi out is reducing, then phase error is increasing. But what you want? You want to decrease it. Okay. So what you have to do? For this, you have to increase this VPD bar. Okay. And how you can increase the VPD bar? You have to stay in this range. Here you can see that VPD bar is increasing. Okay, so you have to increase VPD bar, and VPD bar will increase VC, and this will increase omega out, and omega out will increase this, and finally you would be able to reduce phi error. Okay, so where you have to stay? You have to stay in this range. What range? That is, phase error should be minus pi by 2 to pi by 2. That is the linear range. So in that range you have to stay for reducing the phase error. Yeah. Okay, so let me repeat again. So what we want, our aim is to make phi error minimum or 0. Okay, so for that, what we have to do, we have to increase phi out. Okay, I'm saying the condition is phi error is greater than 0, means phi error is positive, and you want to make it 0. So for that, you have to increase phi out. How can you increase phi out? For increasing phi out, you have to increase VC, and for increasing VC, you have to increase VPD bar. Okay, so that's why I'm saying that you have to stay, if this is VPD bar, this is phase error, you have to stay in this range, in this linear range, and that linear range, in this range you are able to lock your PLL by making phase error constant or 0. Okay, I hope it is clear. And if you are going to this range after pi by 2 you are going, then what is happening? your VPD bar is negative, means VPD bar is reducing, which will reduce VC and which will reduce phi out, or you can say omega out. And this omega out will reduce phi out. Since phi out reducing, so phase error will increase. Why? Because phase error is equal to phi in minus phi out. See, you are decreasing it more, so means it will become more. So that is a problem. So if you want to lock the PLL, you have to stay, this phase error have to stay between minus pi by 2 to pi by 2. Okay. So let it, if this this phase error is staying in um, minus pi by 2 to pi by 2, okay, the PLL can lock, but still there is one problem. So what is that problem? So you know the KPD. KPD is the gain of the phase detector. So this KPD is equal to d by dt of VPD bar. You know VPD bar. VPD bar was 1 by 2 sine phi error 0. So what will be KPD? KPD will become equal to 1 by 2 cos phi error 0. So if you are drawing it, it will be like this. So this is KPD with respect to phi error. So we saw that okay, this is what, this is pi by 2, this is minus pi by 2, and we saw that for VPD this was a linear range. So you will keep this phi error in this range, but what you are seeing, if your phi error is equal to pi by 2, okay, and at that time you are getting the maximum VPD bar, which will be equal to 1 by 2, right? Because pi by 2 this will become 1 and this is 1 by 2, so VPD bar equal to 1 by 2, that is the maximum value of the VPD bar at pi by 2. Okay, at pi by 2 it is getting maximum value. Now if at this is the case, so what is the value of the KPD? KPD is the minimum. What it indicates? It indicates that if KPD is very small, okay, if KPD is very small, then what will be the output of KPD? Then the KPD output, this block response will be very small. Okay, this response will be very small because this value is very small. Okay, so this type of problem is with this type of phase detector. Okay, so this is the issue with the this analog mixer type phase detector. Okay, let's have a uh, discussion again about this PD, a brief discussion. So what we saw, let's discuss that. So we saw that we have a mixer based PD, okay, and we have phase error equal to positive. So for locking the PLL, we have to increase phi out. So increasing phi out, we have to keep VPD bar high. We have to increase VPD bar. Okay. So for this purpose, if I am plotting VPD bar, the waveform was like this. So from this to this range, you can see that VPD bar is increasing. So we have to keep phase error between minus pi by 2 to pi by 2. So if PLL is in, so if phase error is in this range, then you can lock the PLL. And if this is greater than pi, then PLL can't lock. Okay. So that was the first thing. Then the second thing is yeah, if you are at this point, then you are getting the maximum value of the VPD. So it's good, but no, there is one more problem, that is the KPD, which is the differentiation of this. If you are taking differentiation of this, you will got like this. Okay, this red point you can see. This is for KPD. So for this high value of the KPD, sorry, high value of the VPD bar, the KPD value is very small. So the response of the loop is very slow, which is another problem. Okay, so that is the problem with this phase detector. And in next lecture, we will go to more type of the phase detector, which are better than this type. Okay, so for this lecture, that is okay. So thanks for watching this lecture. Hope you like it. So if you have any doubt, you can ask me in this by texting me. Okay, thanks for watching this lecture. Bye.